Hello everyone. Our team, which consists of me, Adriana, Joel, and Zach, will be presenting the oscillating fan. Oscillating fan is a fan that can turn side to side. It provides coolness by circulating the air in a space during warm days. Additionally, the oscillating movement allows better ventilation within larger range of area instead of just one direct spot.
Right. So there are three simple machine components in the oscillating fan. You have the gears, which are in charge of changing the directions of the torque in order to rotate the fan using a four-bar mechanism. You have the bolts and nuts, which are used to secure the structural strength of the fan and also hold the housings together. And also you have a spring that serves as a switch between oscillating and non-oscillating mode of the fan. Moving on. Um, In order to operate the oscillating fan requires an input around 54 watts of electricity, and it can output up to about 1840 cubic feet of air per minute. However, in order to calculate a mechanical advantage, our team decided to estimate it by calculating the gear ratio. Based on the number of gear teeth, the gear ratio of the specific fan is calculated to be 1 over 16, which means the output gear rotates at an angular velocity 16 times smaller than that of the input gear. As a result, the torque provided by the output gear is 16 times larger than the input gear, meaning the mechanical advantage is. Now let's take a closer look at the machine components. So first, let's take a look at the gears. As you can see, there are four gears within the gearbox. You have the blue warm gear that is directly attached to the motor. You also have gear 2 directly connected to the pin through gear 1, so that gear 1 and gear 2 rotate at the same angular velocity. So when the pin is pushed down, gear 2 will be pushed down with the pin and make contact with gear 3. So therefore, when the fan is operating, all four gears will be rotating and achieving that gear ratio of 1 over 16. And the rotation of gear 3 will also drive a four-bar mechanism beneath it, resulting in the oscillating motion of the fan. However, when the pin is pulled up, gear 2 will lose contact with gear 3, meaning that gear 3 will no longer rotate with the other gears. As the rotation of gear 3 is cut, the fan's oscillating motion is also cut. Moving on, we have the bolts and nuts, and these are used to connect the housings of different components. As you can see in the figure, the bolts and nuts are used to connect the housing of the motor. They're used to constrain the motions of components such as the motor and the spring so that it can prevent damage done to the surrounding areas as well as the machines itself. And last of all, we have the spring that serves as a switch. So the spring holds two ball bearings that are pushed against the wall of gear 2 or the gearbox housing to secure the pin in place. When the pin is being pushed down, the spring will be compressed until the ball bearings fit inside gear 2 or the housing. And when it's in place, it will stop being compressed and it will extend itself. The ball bearings will make contact with the wall and therefore securing its location, which means by pulling it up, the pin will not fall down by itself, and by pushing it down, it will not pop up by itself.
Moving on to the free body diagram. There are a total of four gears that are used in the oscillating fan. The worm gear is directly connected to the motor and produces a specific amount of torque depending on the fan's desired speed. The worm gear then transmits its force to the adjacent gear, which is identified as gear 1 in this picture. Since gear 1 and gear 2 are connected in parallel using a crankshaft, there are no forces exchanged between those two gears, but they do have similar angular velocities. Gear 2 then transmits force to the last gear, which is gear 3. Gear 3 is connected to the structure that rotates the fan, so the speed of gear 3 will influence how fast will the fan rotates. Next, we have bolts and nuts. The bolts and nuts seal the housing to the motor structure. In the picture, the first and third layer are the housing plates, and the second layer is the motor structure. The motor structure tends to vibrate when the fan is operated, so it creates a shear situation in which the plates and the motor structures are trying to oppose the motion of each other. The vibration also creates a tension force to the bolts. Lastly, we have a spring. The spring is equipped with ball bearings that slide smoothly through the housing wall when the pin is pushed down and pulled up. While sliding through the wall, The ball bearing exerts compression force on the spring. When the spring is in oscillating or non-oscillating mode, the pin is self-locked and the spring is back to its relaxed length. I'll then pass the presentation to Zach.
So as we said before, there are a total of 4 gears used in the system, including an input worm gear. And gear 1 and 2 serve to change the direction of the angular motion of the worm gear and also decrease the angular velocity. Gear 1 has a large number of teeth in order to further decrease the angular velocity from the worm. So since the motor is connected to the fan blades on the one side and the worm gear on the other, we need a large number of teeth on gear 1 so that the fan isn't oscillating anywhere near as quickly as the fan blades spin, because that would break the fan. Moving on to the bolts and the nuts. So bolts with fine threads have been selected as they have less tendency to loosen under vibration, since the helix angle is smaller than for coarse threads. Fine threaded bolts also have a shorter thread depth, which allows them to be threaded into the thin housing's wall with minimum damage to the housing. As far as the spring goes, so the spring is compressed by normal forces from the housing wall and the bearing, as Adriana said. And in order to switch between the different positions smoothly, the spring constant should not be too large. If it was too large, it could make the fan's pin too difficult to push down, or it could induce unwanted forces on the gearbox cover. The spring index should be between 4 and 12 in order to satisfy the requirements of a helical compression spring. And for our design improvements, we wanted to add screws to the plastic motor / gearbox housing for easier cleaning and maintenance. So many oscillating fans today don't have a screw that holds the motor on. Instead, it's 2 plastic pieces that clip together. And that just makes it very difficult to do any maintenance without breaking the housing. But another idea that we had would be to increase the length of the blades and reduce their widths. And that would gain larger torque. So if the blades are longer but thinner, they'll exert a greater beneficial torque on the motor, which we hope would improve efficiency. And that's all we have as far as the oscillating fan goes. Thank you.